think you understand gravity? Step on a scale. See the number. That's your weight. Earth pulling you down. Simple. Drop something. It falls. Moon orbits Earth. Planets circle the sun. Objects with mass attract each other. Newton figured it out centuries ago. The so-called force of gravity seems easy to understand. Simple. Even wrong. Not a little bit wrong. Fundamentally wrong about what's actually happening. Snorts because gravity isn't a force at all. And when you finally see what gravity really is, when you really see it, the whole universe starts to look different. Let me show you. Stand up right now. Feel your weight. What are you feeling? You say gravity. Earth pulling you down. But think about the actual sensation. The floor pressing against your feet. Pushing up. That's what you feel. The floor pushing. This mysterious pull everyone talks about. You never feel it. Not once. You only feel the push. Always pushing up, never pulling down. So where's this pull? And here's something stranger. The moon is falling toward Earth right now. Has been falling for billions of years, but it never gets closer. Just circles. Always falling. Never landing. What kind of pull works like that? A pull that pulls forever, but never pulls anything in. And according to Newton, that pull happens instantly. Move Earth and the moon feels it immediately across 240,000 miles of vacuum instantly. How? What carries the message? What's the mechanism? Newton himself couldn't explain it. He called it action at a distance, and admitted he didn't understand how it worked. But the mathematics was beautiful. The predictions were perfect. So people stopped asking uncomfortable questions. They shouldn't have stopped. Go back several centuries. Nobody understood how planets moved. Copernicus said they orbit the sun. Fine. But how? What paths do they follow? Tycho Brahe built an observatory and spent decades recording planetary positions night after night, year after year, measuring angles with brass instruments to fractions of a degree. Why such precision? Because you can't understand nature by guessing. You have to look. Measure carefully. Write down exactly what you see. That's where real science begins. His data reached Johannes Kepler. Kepler wanted to find the shape of planetary orbits. He tried circles. The predictions were close, but Mars was off by 8 arc minutes, 863rds of a degree. Most people would shrug that off as measurement error. But Kepler knew Tycho's precision. That man didn't make 8 arc minute errors. So Kepler threw out his theory and started over. After years of work, he found it. Ellipses. Planets move in ellipses with the sun at one focus. Perfect match to the data. Beautiful. But it raised a bigger question. Why ellipses? Meanwhile, Galileo was doing simple experiments. Rolling balls down ramps. Sounds trivial, but watch what happens. Roll a ball down an incline. It speeds up. Let it roll onto a flat surface. It keeps going. Doesn't stop immediately. Now imagine you could eliminate all friction. What would happen? The ball would roll forever. Same speed, same direction forever. This bothered people. Surely motion requires a continuous push. Surely things naturally come to rest. No, that's backwards. Motion is natural. An object moving in a straight line doesn't need explanation. That's the default state. What needs explanation is change. Slowing down, that's friction. Speeding up, that's a push. Changing direction, that's a sideways force. This is inertia, the first law of motion, and it creates a puzzle. Planets should move in straight lines. That's their natural state. But they don't. They curve. Their paths bend continuously toward the sun. Something must be deflecting them every instant. What? Isaac Newton saw it clearly. Planets want to go straight. That's inertia. But they curve. Something changes their motion constantly. He called it gravity. Universal attraction between any two masses. The force depends on mass and distance. More mass means stronger force. Greater distance means weaker force. Specifically, force drops with the square of distance. With this one principle, everything fell into place. Why ellipses? Because planets are falling toward the sun while simultaneously moving sideways. The combination creates elliptical paths. Kepler's laws emerge naturally from Newton's force law, combined with inertia. Why does the moon orbit Earth? same snort principle. It's falling toward Earth, but moving sideways fast enough to keep missing. It falls around Earth instead of into it. Why does an apple fall? Earth attracts it. Same force, same law, just different scale. Newton did a beautiful calculation. He figured out how much the moon falls every second, how much its path deviates from a straight line. Then he calculated how much objects fall on Earth's surface. The numbers matched perfectly when accounting for distance. Revolutionary. The force pulling an apple is the same force holding the moon in orbit. Heaven and Earth, same storch. Physics. With Newton's law, everything made sense. Ocean tides happen because the moon pulls on Earth's water. Earth is round but bulges at the equator because it spins. Comets return on predictable schedules because they follow elliptical orbits. Strange observations found explanations. Jupiter's moon sometimes appeared early, sometimes late. Turned out light takes time to travel. When Earth is farther from Jupiter, light takes longer to reach us. This led to measuring light speed for the first time. Planets wobble slightly because they pull on each other, not just on the Sun. From the wobbles in Uranus's orbit, astronomers predicted a new planet, Neptune, and found it exactly where predicted. For 2 centuries, Newton's law of gravity stood as one of the greatest achievements in science. It explained everything anyone could measure, but there was one detail nobody could explain. Drop a hammer and a feather in a vacuum. They hit the ground at the same time, exactly together. The hammer has more mass. So according to Newton, gravity pulls it harder, much harder. But the hammer also has more inertia. It resists acceleration more, much more. These 2 effects cancel perfectly. Not approximately, perfectly. Every object falls at the same rate, regardless of mass. Why? Newton's theory requires 2 different properties of mass. Gravitational mass determines how strongly objects attract each other. Inertial mass determines how hard it is to accelerate something. And these 2 properties are always perfectly proportional for every substance ever tested to incredible precision. But why should the attracting property of mass and the resisting acceleration property be perfectly equal? Newton had no answer, just the remarkable coincidence that made the mathematics work beautifully. Or was it a coincidence? Einstein asked a different question. What if it's not a coincidence? What if that perfect equality is telling us something fundamental about what gravity really is? Here's a thought experiment. You're in a closed room with no windows. You feel your normal weight pressing you to the floor. Are you on Earth or are you in a rocket in deep space accelerating upward at 9.8 m per s squared? Can you tell the difference? Drop something, it falls to the floor in both cases. Throw a ball horizontally, curved path in both cases. Stand on a scale, same reading in both cases. There is no experiment that can distinguish them. This is the equivalence principle. If you truly cannot tell gravity from acceleration, maybe they're the same thing. Maybe what we call sitting still in a gravitational field is actually a form of acceleration. Here's Einstein's revolution. Objects in free fall have no force acting on them. The falling apple, the orbiting moon, satellites circling Earth, astronauts floating in space capsules, none of them experience any force. They're moving naturally, following their natural paths, no forces, no pulls, nothing acting on them. But the apple is clearly falling. Yes, but what if the apple isn't accelerating at all? What if it's following the straightest possible path, and it's space itself that's curved? This is Einstein's profound insight. Gravity is not a force between objects. Gravity is the curvature of space and time. Massive objects don't pull on other objects. They warp the space around them. They bend it, curve it, distort the geometry. The apple isn't being pulled to the ground. It's following the straightest possible path through curved space-time. But space-time near Earth is curved, so straight points toward Earth's center. You standing on the ground aren't being pulled down. You're trying to follow your natural path through curved space-time, a path toward Earth's center. But the ground is in your way. The ground pushes you upward, preventing you from following that natural path. That's what you feel as weight, not gravity pulling down. The ground pushing up, deflecting you from your natural trajectory through curved space. Einstein made a concrete prediction. If gravity is really curved space, then light should be affected too. Light has no mass. In Newton's theory, gravity shouldn't affect light at all. But if gravity is curvature of space itself, then light following the straightest path through curved space should bend. During a solar eclipse, astronomers measured the positions of stars near the sun's edge. The stars appeared displaced from their true positions. The starlight had bent passing near the sun, exactly as Einstein predicted. This is gravitational lensing. We see it in observations all the time. Now, massive objects bend light from more distant objects behind them, creating distorted images. Direct evidence that space itself curves in the presence of mass. Astronauts in orbit look weightless, floating around. Zero gravity up there, right? Wrong. The gravitational field at the altitude of satellites a couple hundred miles up is almost as strong as here on Earth's surface, about 90% as strong. So why do astronauts float? Because they're falling. The capsule is falling. Everything is falling toward Earth constantly. But they're also moving sideways very fast, about 17,000 miles per hour. As they fall, Earth's curved surface falls away beneath them. They keep missing. They fall around Earth instead of into it. Everything falls together at exactly the same rate. So there's no sensation of falling, no weight, no sense of up or down. It feels exactly like floating in empty space, far from any mass. This is equivalence in action. Free fall in a gravitational field feels identical to floating freely in empty space, because they are the same thing. In free fall, no force acts on you. You are following the natural geometry of curved space-time. Think of Earth's surface. It's curved, but standing on it, it looks flat to you. And here's something remarkable. Why is Earth round in the first place? Because of gravity, but not in the way you think. It's not that some force is pulling everything toward the center, molding Earth into a sphere. It's that space around Earth's mass is curved equally in all directions. Every piece of rock, every drop of water is trying to follow the straightest path through that curved geometry. And when everything follows those curves from all directions equally, you get a sphere, the only shape where every point on the surface is the same distance from the center. Earth is round because that's what happens when matter follows curved space-time. The shape emerges naturally from the geometry. An ant walking what it thinks is a straight line on that curved surface actually follows a curve, but from the ant's perspective it's going perfectly straight. That's what's happening with everything near Earth. Except it's not just space that's curved, it's space and time together. Space-time. Massive objects create curves in space. Depressions, wells, distortions. The sun creates a deep well. Earth creates a smaller one. Even you create a tiny well, too small to measure easily, but it's there. Objects moving near these wells naturally follow the curves. Not because anything pulls them, because they're following the straightest possible paths through curved geometry. The moon orbits Earth because it's following the natural geometry of curved space around Earth. That geometry makes the straightest path into a circle. An apple falls because it's following curved space-time near Earth's surface. In that curved geometry, straight ahead through time points toward Earth's center. When you throw a ball, it follows a parabola, not because gravity pulls it down, because it's moving through curved space-time. And the straight line in that curved space looks like a curve to you. You're standing right now, you feel weight. In Newton's picture, gravity pulls you down and the floor pushes you up. Two forces balanced. In Einstein's picture, only one force acts on you, the floor pushing up. But if there's only one force, you should be accelerating. And you are. You're accelerating upward constantly. The natural path through space points toward Earth's center. That's the free fall trajectory. But the floor is in your way. It pushes you upward, deflecting you from that natural path. You're like someone standing in an accelerating rocket. The floor pushes. You feel weight not from any downward pulling force. From being accelerated away from your natural path, the apple hanging in a tree is also being pushed upward by the branch. When the branch breaks, the pushing stops. The apple is suddenly free, free to follow its natural path through curved space. It falls, but the apple isn't accelerating. The apple is finally free to move naturally. Snorts. You standing on the ground are being constantly accelerated upward by the floor pressing against your feet. Falling is the natural state. Standing still requires a force. That's Einstein's revolution. Once you understand gravity as geometry, extreme phenomena make sense. A star is essentially a massive ball of gas. Its mass creates a deep well in space-time. The natural paths in that curved space point inward. What prevents collapse? Pressure from nuclear reactions in the core pushing outward. Balance. When the nuclear fuel runs out, the pressure drops. Balance breaks. The star collapses. If the star is massive enough, the collapse continues until matter is compressed to incredible density. Atomic nuclei merge. Electrons are crushed. What emerges is a neutron star, nuclear matter compressed to city size. A teaspoon of this stuff would weigh 1 billion tons. For even more massive stars, not even neutron pressure can stop the collapse. Space-time curves so sharply that all possible paths lead inward. Even light cannot escape. This is a black hole. Near a black hole, space-time is so severely warped that light itself, following the straightest possible paths through this geometry, spirals inward and never comes out. We can't see black holes directly, but we see their effects. Matter falling toward a black hole speeds up, heats up, radiates enormous energy before disappearing. All from one idea. Mass curves space-time. Objects follow the curves. From this one principle, everything follows. Planetary orbits, tides, the precession of Mercury's perihelion, a tiny effect Newton's theory couldn't explain, but Einstein's predicts perfectly. Gravitational lensing, black holes, gravitational waves rippling through space when massive objects collide. The same principle explaining how the moon orbits also explains the largest structures we observe. Galaxies, clusters of galaxies, universal, elegant. The pattern in the small piece reveals the design of the whole fabric. Newton's equations work beautifully for practical purposes. We use them to launch satellites, calculate orbits, predict eclipses. They're simpler than Einstein's equations, and accurate enough for most applications, but Einstein revealed what gravity actually is, not a mysterious force pulling objects together across empty space, the curvature of space and time themselves. Mass tells space how to curve. Curved space tells objects how to move. When you step on that scale, you're not measuring a downward pull. You're measuring how hard the scale must push to prevent you from following your natural path through curved space. When you watch something fall, you're seeing an object finally free to follow the geometry that mass has woven into the fabric of reality. When you look at the moon, you're seeing an object following the straightest possible path through the curved space around Earth. A path that looks like a circle because space itself is curved. Space brings objects together. That's what we call gravity, not a force, geometry. And that is far more beautiful than any mysterious pole could ever